Okay, so here we go. So we've been looking at our linear measurements over the last week or so. And we had like 4 feet. If I wanted to convert that into inches, what did that become? 48 inches. Good. Or if I have 7 yards and I want to convert that into feet, what's that going to become? How many feet are... There we go, 21 feet. Now, if we didn't know those off the top of our head like that, the process to go through to do that formal conversion, for example, our 4 feet into inches, we could have done 4 feet over 1, make it a fraction, and then we are changing feet into inches. So to get rid of feet, since it's on top of a fraction here, we'll put it on bottom of the fraction in our conversion factor. So it'll cross-cancel out in our math. So we'll put inches on top. 1 foot is 12 inches. So now the feet do cross-cancel when we multiply. 4 times 12 inches is the 48 inches. On bottom, 1 times 1 is 1. So 48 inches over 1, or just 48 inches. Down here for our yards, we could have done the same thing. 7 yards, put it over 1 to make it a fraction. In our conversion factor, we're getting rid of yards, so they're on top here. We put them on bottom here, so they'll cross-cancel out. We're converting into feet. 1 yard is 3 feet. So the yards do cancel out. 7 times 3 feet is 21 feet. 1 times 1 is 1, so 21 feet over 1 are just 21 feet. Now we looked at some conversions that were more difficult than that. We might have 198 feet going into rods. Can anybody tell me what that's going to be? Not one that most of us know off the top of our head, is it? But if we go ahead and set it up, 198 feet over 1. In my conversion factor, what unit goes on bottom? Feet, because that has to cancel out the other feet. What's going to go on top then? Well, I'm changing it to rods. What's my relationship between feet and rods? First of all, which one's larger? Which one's a bigger unit? The rod. So we almost always make the larger unit 1. How many feet are in a rod? 16.5. Good. So now, let's get back here. The feet do cancel out. We have 198 times 1 rod is 198 rods. Over 1 times 16.5 is 16.5. And this one, since it's not a 1 on bottom, both of these were 1 in the denominator. Since this one is not, we have to divide it out. 198 divided by 16.5 is 12 rods. You could have seen there, as we're doing this, that since the 198 is on top and the 16.5 is on bottom, you're going to multiply by the 16.5. So if you see that pattern, you can just go ahead and do that instead of multiplying across and dividing it out later. I want to throw a little bit of a wrench in this today. What's different about this? It's not 3 feet into inches, it is square feet. 3 square feet, or 3 feet squared, into square inches, or inches squared. Does 1 square foot equal 12 square inches? And the first reflex is probably to say yes, but let's take a closer look. 1 square foot is defined to be a square that is 1 foot by 1 foot. 1 foot on each side. Well, 1 foot is 12 inches. So it is 12 inches on each side. So using the basic areas that we already know, to find the area of this, you do length times width, 12 times 12, which gives us how much? 144 square inches. So as we mentioned briefly on Friday, 1 square foot is 144 square inches. So to convert this over here, I put my 3 square feet on top. Over here, my conversion factor, square feet have to go on bottom, so they cancel out. Square inches on top, because that's what we're converting to. And I use this equivalency now. 1 square foot equals, not 12, but 144 square inches. So the square feet cancel out. It's all ones on bottom. 3 times 144 square inches is 432 square inches. Oops, I got a 2 in there instead of a 3. There we go. Now, one of the things that people get confused about on these is a lot of people want to square the 3. Does this squared here operate on that 3 at all? No, it doesn't. The squared is operating on the feet. That is telling us that this is not regular linear feet, it is square feet or units of area. So this squared here does not affect the 3 at all. A lot of people want to square that 3. Resist the urge to do that. Don't do it. The squared only is telling us that these are not regular feet and inches. They're not regular length units. Now, of course, what it does affect, as we saw here, is the conversion factor, the equivalency. It is no longer 12 inches it is still 12 inches in a foot, but it's square inches in square feet. It's 144 square inches in a square foot. So be careful with those. So, with that in mind then, 567 square feet is how many square yards? Well, obviously we got square feet over 1, and in our conversion factor, square feet are going to go on bottom and square yards on top. But how many square feet are in a square yard? Well, it's the same type of thing. 1 square yard is defined to be 1 yard by 1 yard. How many feet are in a yard? 3 feet in a yard. So this is 3 feet by 3 feet. So 1 square yard is equal to how many square feet? 3 by 3 is 9 feet squared, or square feet. So back over here, 1 square yard is 9 square feet. So we're going to take a little shortcut here. The square feet cancel out. 567 divided by 9 is going to give us, what, 63 square yards. So in your notes, I want you to figure out for me 3,456 square inches. How many square feet is that? And then also 17 square yards. How many square feet is that? So take a couple minutes and figure those out. Okay, so for the first one, 3,456 square inches. Put it over 1. Over here, square inches have to go on bottom. We're converting to square feet. What's our relationship between square inches and square feet? 1 square foot is how many square inches? I heard somebody mumble it there, 144. So the square inches cancel out. And since the 144 is on bottom, we're going to divide by that. Should give us 24. There it is, 24 square feet. How many of you had 24 square feet? Oh, good share of you. Good. Now for the next one here, 17 square yards into square feet. In our conversion factor here, square yards have to go on bottom so they cancel out. Square feet on top. What's our relationship? 1 square yard is how many square feet? 3 by 3 or 9. So the square yards cancel out. 17 times 9 is what, 153 square feet? Does that look right? Yep. Okay, any questions on those? Okay, now there is a unit that we're going to introduce that you've probably all heard. That is part of our area units, and that is the acre. The definition of an acre actually originated from rods because it was part of surveying. 1 acre is originally defined to be 160 square rods. Well, okay, we don't use rods that much anymore, so how do we convert this into square feet? Well, we have to first figure out the equivalency between square rods and square feet. We know that 1 rod is how many feet of length? 16.5, yes. If it's square rods and square feet, what we saw up above is we can just square each piece of this. Of course, 1 squared is 1. A rod squared is a square rod. 16.5 squared is 272.25, I believe. And feet squared is just a square foot. So 1 square rod is 272.25 square feet. So let's convert this. 160 square rods over 1. Square rods on bottom. 272.25 square feet on top. 160 times 272.25 should give us 43,560. And that is true. There's 43,560 square feet in 1 acre. There's also a very close relationship between an acre and a square mile. A little bit about land division. Land is divided off into 1 square mile sections. And within a square mile section, it's divided up in 4 pieces in each direction. So 16 total pieces. So each piece is 1/4 mile by 1/4 mile. Each piece is what we call a 40 or 40 acres. So if you look at that, there are 16 of those. 40 times 16 is 640 acres in 1 square mile. So let's do just a little bit of basic area here quick. So let's say you go to buy a city lot. And that city lot is 90 feet by 120 feet. You want to know how many acres that is. Well, our basic area is 90 times 120, which is 10,800 square feet. Well, how many acres is that? Well, 10,800 square feet, we'll put it over 1. Square feet on bottom, acres on top. 1 acre is 43,560 square feet. So the square feet cancel out. This is telling us since the 43,560 is on bottom, it's telling us we're going to divide. So we've got 10,800 divided by 43560. Gives us 0.248 basically acres. So that would be a 1/4 acre lot basically. Any questions? Okay, let's jump up to the metric system. In the metric system with our units of area, let's review our lengths first. So we have meters, decimeters, centimeters, and millimeters. Over here, decameters, hectometers, and kilometers. And when we converted in the metric system, it was just a matter of moving the decimal point. If I have 1.9 meters and I'm converting it into centimeters, I'm just looking at my chart and realizing from meters to centimeters, it's 2 spots to the right. So my decimal point here moves 2 spots to the right, 190 centimeters. The reason that worked is because each spot on this chart for our metric units or metric prefixes is either multiplying or dividing by 10 every time we move from one unit to the next. And when we multiply or divide by 10, it simply moves a decimal point 1 spot to the left or to the right. Well, if I want to do 1.9 square meters into square centimeters. Well, now that we've watched this happen with the standard measurement system, it might be a little easier to figure out what's going on in our metric system. In the standard system, each one of our conversions was squared. 1 foot is 12 inches, but 1 squared foot was 12 squared, or 144 square inches. 1 yard is 3 feet, but 1 square yard is 3 squared, or 9 square feet. So the same thing's going to happen down here with our metric system. As we move 1 spot to the right, instead of multiplying by 10, if it's square units, we're going to multiply by 10 squared, which is 10 times 10 is 100. When we multiply or divide by 100, it moves the decimal point 2 places. So now, because these are squared units, every position we move on the chart is going to be 2 decimal places. So meters to centimeters is still 2 places on the chart, but because these units are squared, we double that. So it is now 4 places of the decimal point. So 1, we have to add zeros, 2, 3, 4. So that is 19,000 square centimeters. So I have 720 millimeters squared going to centimeters squared. From millimeters to centimeters is 1 spot to the left. How many spots do we have to move our decimal point? Because it's squared units, we have to go double, which would be 2. 1 spot to the left on the chart means 2 spots to the left with our decimal point. So from here it goes 1, 2. That's 7.2. So if we have 38,000 centimeters squared going into meters squared. Do that one in your notes quick. And 51 centimeters squared going into millimeters squared. Do that one in your notes quick. So from centimeters to meters is 2 spots to the left, but because it's squared, we have to double that, so the decimal point goes 4 spots to the left. 1, 2, 3, 4. So that becomes 3.8. Centimeters to millimeters is 1 spot to the right. But again, because it's squared units, we have to double that. So we go 2 spots to the right. Filling in zeros, it is 5,100 millimeters squared. Any questions on those? Okay. Well, the next step I want to take, by the way, there is a unit of area in the metric system, similar to an acre. It's called an R. An R is actually defined to be, I'm trying to remember what it was it 10 meters? You know what? I was right. An R is defined to be 100 meters squared, or 10 meters by 10 meters. That is, hey guys, you got to keep down the paper shuffling. Okay. So in the metric system, their equivalent to an acre is that 10 meter by 10 meter. Of course, that's much smaller than an acre. If we wanted to compare that to our acres, we have the metric equivalents. We went over those a little bit last week. If I want to convert 10 meters by 10 meters into feet, let's do that. Let's convert 10 meters into feet and then figure out the area. Well, I'm going to do this. 10 meters is 1,000 centimeters. Just moving my 2 decimal places on the chart. I'm going to convert that into inches, 2.54 inches or centimeters in 1 inch. So the centimeters cancel out. Then I'll do the conversion into feet. 1 foot is 12 inches. So the inches will cancel out and will be in feet. So what will happen here, I've got my 1,000 centimeters, or my 10 meters, divided by 2.54 and then divided by 12. So I get 32.808. So that R is 32.808 feet on each side. If I square that, that means 1 R is 1,076 square feet. We'll go 0.4. Now remember, an acre is 43,560 square feet. So how many R's are in an acre? Well, 1 acre, again, 43,560 square feet. An R is 1,076.4 square feet. So here you can see the acres cancel out, the square feet cancel out, and we will have just R's on top. So here we're going to do this. We start out with just 1 acre. The 43,560 is on top, so we're going to multiply by it. And the 1,076.4 is on bottom, so we'll divide by it. So 1 times 43,560. Obviously, you don't really need to do the 1 times. Divided by 1,076.4. Which tells us that 1 acre is actually 40.47 R's. So that metric unit of area, the R, is very, very small compared to our acre. A 40 would be over $1,600, by the way. Okay, so enough of that. The next step, we've done our area conversions. Let's take a look at volume conversions. Cubic feet. If I want to convert 2 cubic feet into cubic inches. Now, of course, we've said there's 12 inches in a foot, but there's not going to be 12 cubic inches in a cubic foot. 144 is the number of square inches in a square foot. That's not going to work here either. We look at our definition of a cubic foot. It is 1 foot by 1 foot by 1 foot. It's a cube that's 1 foot in every direction, right? So 12 inches by 12 inches by 12 inches. If we multiply that out, 1 cubic foot is how many cubic inches? 12 times 12 times 12 is?
144.
Careful. Yeah, you got to do one more 12. 1,728. So 1 cubic foot is 1,728 cubic inches. So 2 cubic feet, put it over 1. We'll put our cubic feet on bottom here. 1,728 cubic inches on top. So the cubic feet cancel out. 2 times 1,728 is 3,456 cubic inches. Well, what if we have 5 cubic yards and we're going into cubic feet? Well, it's the same thing. A cubic yard is defined to be a cube that is 1 yard by 1 yard by 1 yard. How many feet are in a yard? 3. So this is 3 feet by 3 feet by 3 feet. So this one you should be able to get for me. 1 cubic yard is 3 times 3 times 3, or how many cubic feet?
27.
27. Very good. In construction, this is actually a huge conversion. When you order concrete, you may hear people say, oh, I ordered 7 yards of concrete. What they're talking about is 7 cubic yards. But when you measure stuff up, you're generally going to be measuring it in feet and calculating cubic feet and having to convert that cubic feet into cubic yards. So anyway, over here, 5 cubic yards over 1. Yards cubed go on bottom, so they'll cancel out. Feet cubed on top. 1 cubic yard is 27 cubic feet. Cubic yards cancel out. 5 times 27 is 135 cubic feet. So I'm going to have you guys try a couple here. (6,912) cubic inches is how many cubic feet? 567 cubic feet is how many cubic yards? Give those a shot in your notes quick and we'll talk about it. Okay, so 6,912 cubic inches over 1. What's our conversion factor going to be here? Cubic inches on bottom, cubic feet on top. Cubic feet obviously is the bigger unit. How many cubic inches in a cubic foot? There you go, 1,728. Good. Cubic inches cancel out. Since the 17/28 on bottom, we will divide. That gives us 4 cubic feet, correct? So then over here, 567 cubic feet over 1, going into cubic yards. So cubic feet on bottom, cubic yards on top. The bigger unit is the yard, so it's 1 cubic yard. How many cubic feet are in a cubic yard again? (27), yes. Remember, it's 3 feet in the yard, so it's 3 by 3 by 3. 3 times 3 times 3. So the cubic feet cancel out. This one's going to be divided by 576 divided by 27 is 21 cubic yards. Any questions on those? Okay, now of course that's going to also translate into our capacities when we get to them, but we'll cover those in a week or so. In the metric system then, at this point you should either have this chart memorized or have it written down somewhere where you can get to it really quickly, like in your back cover or something of your notebook where you don't have to go digging for it. Because you're going to use this chart a lot this semester, or over the next few weeks at least. Do you guys want me to give you a minute to write that down? Sure. Okay, so now, if you recall, 2.1 meters going into centimeters. Now these are just regular meters and regular centimeters. So to get from meters to centimeters, we're going 2 spots to the right. Our decimal point goes 2 spots to the right. We fill in the missing 0. So it's 210. But if we change this to 2.1 meters squared going into centimeters squared, how did that change the way we moved? Well, we still moved 2 spots to the right on the chart, but because it's squared, what did that do to our decimal places? 2 spots on the chart becomes how many decimal places? We double it, right? So it's going to be 4 decimal places. So 2 spots on the chart, we have to move the decimal point. 1, 2, add zeros, 3, 4. That 2, or because the units are squared, we have to double the number of decimal places we move. That's 21,000. What if there were 2.1 meters cubed? What do you think that's going to do to our decimal places? Well, now each decimal place is going to be not multiplying or dividing by 10 anymore. It's going to be multiplying or dividing by 10 cubed, which is 10 times 10 times 10 is 1,000. So when we multiply or divide by 1,000, it moves the decimal point 3 places. So when we have cubed units on our metric links, now every position on the chart becomes 3 decimal places. So we have to triple that number. So 2 spots to the right on the chart becomes 2 times 3, or 6 spots to the right with our decimal point. So we go 1, and then we have to fill in zeros, 2, 3, 4, 5, 6. That is 2,100,000 cubic centimeters. So if I have 2,800 cubic millimeters, I'm going to cubic centimeters. Millimeters to centimeters is only 1 spot to the left on my chart. How far does my decimal point have to move? Well, because these are cubed, every position on the chart is how many decimal places? 3. So 1 spot to the left on the chart, my decimal point has to go 1, 2, 3 spots to the left. That becomes 2.8 cubic centimeters. If I have 56.3 centimeters squared going into millimeters squared. From centimeters to millimeters, it's only 1 spot to the right. Now this one's not cubed, it's squared. So when I square it, what do I have to do to the number of places I move? We double it. 1 spot on the chart becomes 2 decimal places. So we go 2 decimal places, filling in the missing 0. That's 5,630 square millimeters. What if I have 280,000 centimeters cubed? Now it is cubed again. Into meters cubed. From centimeters cubed to meters cubed is 2, or centimeters to meters on the chart is 2 spots to the left. But since it's cubed, we have to triple that. So it's going to be times 3. So 2 spots to the left becomes 6 places of the decimal point. 1, 2, 3, 4, 5, 6. So it's 0.28 meters cubed. Any questions? Okay. Now, as I said, there's going to be units of capacity that we're going to talk about in a few classes, like gallons, liters, and stuff like that, that are related to these units of volume. For now, though, we're going to concentrate on our units of area a little bit more and how we calculate with areas. We've talked a little bit back at the beginning of the semester about basic areas with rectangles. And the area of a rectangle is the length times its width. And in fact, that comes from just our basic building blocks of geometry. We can take a point, pull it in a single direction to create a length. Then if we take that length and we slide it in a second direction that's perpendicular, or at a right angle to the first, if you think of dragging a stick across the sand, it traces out that rectangle. So it makes sense that the size of that rectangle depends on the length of the original stick and the distance that we moved it. And that distance ends up getting called the width. Now, depending on how we look at it, that distance can sometimes be called a width, sometimes it's called a height. An alternative definition of area for a rectangle is base times height, where the base, not necessarily the bottom of the figure, the base is that length that it is based off of, that length that was pulled or moved in order to create the rectangle. So if I have a rectangle that is 8 inches by 13 inches, its area is going to be found by doing what? 13 inches times 8 inches. 13 times 8 gives us 104 square inches. You with me, guys? Okay. Now, this is a rectangle. Of course, for a rectangle, all these corners have to be square corners or right angles. To signify that that's a right angle, to symbolize it, we just put that little square in the corner. What if it's not a rectangle like that? What if we don't pull the stick straight? What if we have our stick like this? Instead of pulling it straight, We pull it at an angle, but we keep the stick parallel to its original orientation. Well, the area, oops, I missed that. The area is still that original length times a distance, but the distance is always measured perpendicular. So this is our distance, or sometimes called our height or our width of this. This is what we call a parallelogram, by the way. Parallelogram means opposite sides are parallel, but the corners are not right angles. It's like a squished rectangle. So if this length is still 13 inches, and the distance between where we started with that side and where we stopped with it when we pulled it is still 8 inches, the area of this is still 13 inches by 8 inches, or 104 inches squared. In fact, we don't even have to pull that piece, that segment, straight when we do it. If I start out with that 13-inch segment again, and this time when I pull it, I'm still going to make sure I keep it parallel to its original orientation. I might pull it off to the side and back and kind of swirl it like that as I go. So it looks like that. This is still, the area of this is still just measured by the length of that original stick, or that original length, times the distance I moved it. And that distance is just measured perpendicular to both of those endpoints. So that's 8 inches. So the area of this is still 13 inches by 8 inches, or the 104 square inches. Now, when you first look at this, it doesn't seem to make sense. But the more you look at it, the more it does. If you look at it this way, I'm kind of a simple little glimpse into calculus. If I think of this rectangle as being a bunch of really, really thin rectangles being stacked up. And by really thin, I mean paper thin, to the point where they really don't have any width at all. Well then, to create this parallelogram, I can just take those rectangles and slide them off of each other just a little bit, like this. Is it going to take any more rectangles or less rectangles to stack up to that same height? No, the width of each individual one is still the same here. So it still takes the same number of them to stack up. So the area of all those little rectangles stays the same, and it takes the same number to cover it. Even for this one, the number of little rectangles it takes is still going to be the same amount. They're just kind of pushed back and forth in the pile a little bit, messed up the pile. So as long as we have a base or a line that's based off of, that we usually call a length, and a distance that has been moved, we can find an area of a shape. Now the next step is to look at something like this. A right triangle. So let's say this is still 13 inches, and this is still 8 inches. To figure out the area of a right triangle, well, we can't take the bottom of this and slide it to make the triangle, can we? So what we have to do is we take that bottom, oops, that's not what I want to do. We take that bottom edge and we slide it, and it creates a rectangle. So the area of that triangle has to be found using the related rectangle. The related rectangle is the rectangle that contains that triangle and has the same base as the triangle. So the area of that triangle is related to that rectangle. Length times width, or base times height, however you want to do it, 13 inches times 8 inches. But it's not that's not our area of the triangle. The triangle is half of the rectangle. So we have to divide by 2. So that's going to give us 52 inches squared for that triangle. So what if we have 9 feet by 8 feet in our triangle? How do we find our area? Length times width, base times height, 9 feet times 8 feet, divided by 2. Or you might have sometimes heard 1/2 base times height. So 9 times 8 divided by 2 is 36 square feet. Again, that comes from the fact that that rectangle would be 9 times 8. The triangle is half of that, so we divide it by 2. Well, a triangle does not have to be a right triangle. We can have a triangle that looks like this. Oops, that didn't turn out well. It looks like this. Let's say that this is 20 inches long. We're still looking for the related rectangle. The related rectangle would look like this. So we need to know the height of that rectangle. Well, on the triangle, the feature, the dimension that shows that would be the distance from this vertex that's the furthest away from our base down to the base at a right angle, of course, because distances are measured at a right angle. That is what we call the height, or sometimes called an altitude, of our triangle. Let's say that that distance here is 6 inches. So then the area of this triangle in black, it's still half of that rectangle. That rectangle is 20 inches by 6 inches. The area of the triangle is going to be that divided by 2. So that comes out to be 60 inches squared. So looking at this triangle here, if I tell you that this is 18 feet across the bottom and 15 feet here, find its area for me in your notes. So the area of that is going to be found base times height, 18 feet times 15 feet, divided by 2. 18 times 15 divided by 2 is what? 135, and of course, feet times feet is feet squared, square feet. A little bit more confusing is a triangle that looks like this. Let's say that this here is 12 feet across the bottom. The height of this, or the altitude, is found by doing this. That's a right angle. We extend that base out so that it goes below that furthest vertex. And we extend up at a right angle. And this is defined to be our altitude, or height. Say that's 5 feet. Looking at that, at first it can be very difficult to see that as being related to, or half the area of, our related rectangle. But if we looked at it like this, with a second rectangle, if we did some subtracting areas, it would work out. I don't want to confuse you, so we're not going to do it. But I'm going to leave that idea out there, that the area of the brown rectangle here is the area of the whole big rectangle minus the green one. And then we do the same type of thing with the triangles. So anyway, the area of that black triangle is found taking base times height, 12 feet times 5 feet, divided by 2. So 12 feet times 5 feet is 60, divided by 2 is 30 square feet. Any questions? Okay, well, another shape that we want to deal with is called a trapezoid. Probably one of those terms you've heard and forgotten about. A trapezoid is just a four-sided figure where two sides are parallel and the other two sides are not. So you can see here, these two sides are parallel with each other and the other ones are not. Let's take a peek here at this. Let's say that the distance between these two, the two parallel sides are called bases. You can call them base 1 and base 2 if you want to, or the short base and the long base. It doesn't really matter. Let's say that the top of this is 18 inches. Let's say the bottom of this is 30 inches. Let's say the distance here, we'll call that 10 inches. Well, when we're working with triangles to find their areas, we related it to a rectangle. For a trapezoid to find its area, we're also going to relate it to a rectangle. To turn this into a rectangle, here's what we're going to do. We're going to go halfway down this slanted side, and we're going to cut that off at a right angle. If we flip this little piece up that we cut off, it should fill in this little spot perfectly, and we now have a squared end on that trapezoid. We'll do the same thing here. We'll go halfway down the slope, and we'll cut this off at a right angle. Flip up that little piece we cut off, and it fills it in. We now have a perfect rectangle. The height of this rectangle is still the 10 inches that it was before. It's the length of this rectangle that's the issue. The length of that rectangle is between the shorter base of 18 and the longer base of 30. In fact, it is exactly halfway between. So the length of this rectangle that we've created is the average of those two bases. 18 plus 30 divided by 2. So that's the length that we've created here. To find the area, it's that average of the bases, 18 plus 30 divided by 2. That gives us the length of our rectangle, times our height of 10. So 18 plus 30 is 48. Now, if you're doing this on your calculator, by the way, a word of advice. You do 18 plus 30, make sure you hit equals before you divide by 2. 18 plus 30, then divided by 2 should give you 24. If it gives you 33, that means you didn't hit equals before you divided by 2. So 18 plus 30 divided by 2 is 24. Times 10 is 240. And these are in inches, so this area will be in square inches. So the generic formula here, the area of a trapezoid, is the little base plus the big base divided by 2. In other words, the average of the bases times the height. So in your notes, for this trapezoid, let's say that this is 8 feet. This down here is 30 feet. And this is 20 feet. Find the area of that trapezoid. So the area is going to be the average of the bases. So 8 plus 30 divided by 2. And then times the height. 8 plus 30 is 38. Divided by 2 is 19. Times the height of 20 is 380. Those are in feet, so this will be in feet squared, or square feet. Now, before we finish up here today, I want to talk about circles. There are some features of the circle that we've talked about. The radius is the most important one, which is just the distance from the center of the circle out to the edge of the circle. There's another feature called a chord. A chord just connects any 2 points on the circle. A chord that happens to go through the center of the circle is called a diameter. Now there's a relationship between the radius and the diameter. The diameter happens to be twice the radius, so 2 times the radius. Because if you think about it, since it goes through the center, you got a radius on each side there. So 2 of them make the diameter. The distance around a circle is called the circumference. And there is a ratio in our circles that relates that. We talked about perimeter a few weeks ago, so we brought this up. The circumference is that ratio that we call pi times the diameter. Pi is defined to be the circumference divided by the diameter. So to reverse that, we can do the diameter times pi to get back to the circumference. If I want to find the area of this, let's take a circle with radius here, and I'm going to call that radius r. The circumference is pi times the diameter, or since the diameter is just 2 radii, 2 times the radius, I can think of it as 2 times pi times the radius, because 2 times the radius is the diameter. So the circumference of this circle, the distance around, is 2 times pi times the radius. What if I cut this circle in half? What then would be the distance around half the circle? Well, that would just be pi times the radius, right? If I divide that by 2, it would just divide out the 2's. So now if I take that half circle, cut it into really thin slices, I mean as thin as I can possibly cut them, and fan them out. And these little sawtooth looking things. Pretend those are even. This distance here is just the radius of the circle. This distance here is the distance I had around here if I cut these thin enough. Pi times the radius. Well, I still have half the circle here. If I cut that into equally thin slices, and I fill them in between my teeth here, it should fill that in perfectly and make this a solid object. This is now, if I cut these thin enough, basically just a rectangle. This is the length of pi times radius. It has a width or a height of the radius, so its area is pi r times r, or pi r squared. Now that's kind of the long way to get to it. Most of you probably already know that the area of a circle is pi times radius squared. But I wanted to show you where it comes from. Basically what we did here, this is kind of the basic theory of calculus, by the way. Cut stuff into thin enough slices so that you can rearrange it and make it into rectangles to find its area. Okay, so anyway, let's take a circle and find its area. So let's say I have a circle here with a radius of 5 feet. Its area is going to be pi. Do you remember what we used for pi? What number we used? Perfect, 3.14. And as I said, if you have that pi key on your calculator and you want to use it, that's fine. I will do the answer keys on all my quizzes and tests both ways. I'll do it using 3.14 and I'll do it using the pi key. So it's going to be 3.14 times 5 squared. Well, 5 squared is 25. 3.14 times 25 is 78.5 square feet. I'm going to have you guys try one. So I have a circle here with a diameter of 8 inches. Find the area of that circle in your notes for me. How many of you caught what I did there? How many of you did pi times 8 squared and got 200.96? Good. It should be pi times what squared? 4 squared. Good. 8 is the whole diameter. Area is pi times radius. So the radius is half the diameter, or 4. Pi times 4 squared is 50.24. That's in inches, so this will be square inches. So we've got our basic areas down for our basic shapes. I want to talk a little bit more about these unit conversions, measurement conversions we've been doing. You know, we had 5 rods, and to convert it into feet, we use that conversion factor. 5 rods over 1. Put rods on bottom, feet on top. 1 rod is 16.5 feet. The rods canceled out. We have 5 times 16.5, which is 82.5 feet. So 5 rods is 82.5 feet. This is what we call, the technical term for what we did there is called dimensional analysis. Dimensional analysis can be used in 2 ways. One, it can be used in our calculations. If we carry through the dimensions with our calculations and we cancel and combine, it tells us whether we did it right. For example, if I'm doing area, if I'm trying to find my area in square feet, if I look over here, 3 feet times 8 feet, well, 3 times 8 is 24. Feet times feet is square feet. So at least that tells me that's a reasonable calculation. I multiplied feet by feet and I got square feet. If I'm looking for my area still in square feet, but I have 2 yards times 5 feet, is that going to make sense? No, yards times feet do not make square feet. So I'd have to adjust one or both of those measurements. It can also be used, we mentioned this before, speed. Let's say that you're driving your car at 60 miles per hour. I know none of you ever go that fast because the speed limits are all 55 around Clayton, right? Sure. So anyway, 60 miles per hour, we can think of that as 60 miles over 1 hour. Just like we put our other measurements over 1, we do that here, only there's hours in the denominator of our units. If I want to find out how long would it take at that speed to drive 300 miles? Now, most of you know how to handle this because we're used to dealing with speeds to do calculations. But if we didn't know, we know that in our answer, we want to have miles, or we want to have, it says how long. So we know we want to have a time on top. So the only time here is hours. We want hours on top in our answer. So we have to either start out with hours on top or do something that's going to put the hours on top. So here's what I'm going to do is I'm going to start out with 300 miles and I'm going to make a unit conversion from miles into hours because I can treat this, we mentioned this before, I can treat this 60 miles over 1 hour as an equivalency. That is saying 60 miles is equal to 1 hour of time. So over here, to change the miles into hours, I'm going to put miles on bottom, hours on top. 60 miles is equivalent to 1 hour. So now the miles cross cancel. My only units left are hours, and I have 300 divided by 60 is 5 hours. So the units on our measurements can tell us exactly how to calculate. Do we multiply, do we divide, or what? Here this is telling us, yeah, we had to divide by the 60 in order to get from our distance to the time it's going to take. Okay, I think you guys have had enough for one day. I'll give you guys the last 15 minutes to get started on some homework. There are a few pages here, actually 4 pages out of the big book and a couple sections out of the little book. So in the big book, you are looking at page 249, exercise 8-5, do the odds on that. Page 250, exercise 8-6, do the odds there. Page 269, exercise 9-5, and page 270, exercise 9-6. These are all just converting with units of area. So the acres might come into there as well. Also in the little book, I would like you to look at units 21 and 22. And again, just do the odd numbered problems in those as well. Those are dealing with areas of rectangles, triangles, circles, and trapezoids. So like I said, you guys can have the last 15 minutes to get started on that homework.